Next trig physics application. Mass hangs from two ropes that form these angles, W and Z. Right here with the horizontal, there's W, there's Z, and each of these ropes have a tension in them. Now, tensions are forces because they are pulls, and if you're not sure how to understand it being a pull, imagine we put one of these spring scales along this rope somewhere, maybe between the rope and the ceiling. The rope's tension would be pulling on the hook, and the spring scale would show you how many newtons of force that rope is exerting on the scale. So that is tension. We are going to find the vertical and horizontal components of each tension, and we're going to use that to solve a problem. So here is the picture broken down a little bit better into, I'm going to put it over here, into each one of these tensions is broken down into a horizontal and vertical components. We're going to use our trigonometry, our SOHCAHTOA, to be able to label those sides. So this picture is a little bit busy, but let's go through it. We're just going to take just this portion of the diagram and explain each part. Here is the tension in this rope. I've taken away the W. I've removed that so that we can see the picture a little bit better. You're welcome. This vertical component is the tension in the rope times the sine of the angle W, which would be right in there. Sine goes with the opposite side of the angle. Cosine, which goes with the adjacent side of the angle, belongs to this side of the triangle that we form. And here we have it as the tension times the cosine of W. Now if we flip over to the other side, it's very sort of symmetrical here. The opposite side is T sub Z of the sine of the angle Z, which is right there. And here we have T sub Z cosine of Z. Now, I'm going to ask a question about the weight of this traffic light. But first I want to just do a quick aside here. If this is hanging and it is not, well, it's not moving up and down, it's not moving side to side, then these two tensions, so this tension here that's pulling to the left must be equal to this tension pulling from the right. And now we're going to talk about the question I have is more about the up-down components. So here is the question. Actually, let me take this and move it away. Here's the question we're going to answer. What is the weight in newtons of this traffic light given the tensions and the angles of the ropes in the system? So this tension is 40 newtons, this tension is 21.3 newtons, and we have these angles of 70 and 50. Okay, first, it should make sense that the larger angle has a greater tension. This was covered in some of the videos when the man moved across the scaffolding. But we'll take these numbers as given for a moment, and we're going to use this model right here. So let's just be clear that it looks like there's only two forces in this picture acting on the system, but in fact there is still gravity. So let me draw the gravity here. This gravity is also a force, and it's a pulling force, and it pulls straight down on this. We could put the arrow here because it pulls straight down on the on the traffic light, or we could just put it right here at the nexus of all the vectors and just think of all of these tensions acting directly at that point. It makes it a little bit easier. So this downward arrow, this force of gravity, this pull must be equal to these two tensions, vertical components. So we have a vertical component of, say, the 40 newtons, and then we add to that the vertical component of the 21.3 newtons. So I'll let you have a go at that. First, just remember that this came from, that's where this came from in the picture. I'll put the picture up before. They're all right there. Okay, here is the answer. Or here's the first part of the answer. The upwards tension of the 40 newtons is 40 times the sine of 70. And this one here is 21.3 times the sine of 50, which is 16.3. If your computer is not in degrees and it's in radians, well, you're going to have a problem. So moving on, here is our final answer to the question. See if I can fit that right. I'm not fitting it right. Okay, well, there's your final answer. The force of gravity on this street light is the weight, which is 53.9 newtons. Okay.